But you can definitely see that we have a really large stretch at the bottom and almost no stretch at the top. Ow! Oh, it broke. Huh. Oh. It broke in two places, and it's just about to break again. Mr. Valeda here in my driveway, and I want to do a little demo regarding swinging a heavy object around in a vertical circle. Don't try this at home, but I'll try it at my home. Watch for the outtakes. I might post separately when it didn't go so well. Alrighty, here we go. So, I've got this 5-pound weight and a bungee cord. Notice how the regular stretch of the bungee is about like this, but then under gravity, it stretches the bungee. All right, I'm going to swing it in a vertical circle. I hope you'll be able to see the difference in the tension in the bungee, which is our way of measuring the force at different spots. Ready? Here we go. Oh, wait a second. Let's get this circle going. There we go. There we go. Oh, this is heavy. Not a great circle, but I think you can see it's really stretched at the bottom and really not stretched at the top. And it's getting spun up as well. Ooh. Okay, so we saw it stretched up like this at the bottom, and we saw it kind of like this at the top. Good, it worked, but let's try to analyze the forces and figure out what's happening. And yes, I'm wearing my frumpy shark thin pajama pants. Don't judge. All right, let's have a quick look at the free body diagrams. So, I decided to look at 4 points, top, bottom, and the two sides. Make sure it's all okay on the camera. And I threw gravity in already. So let's look at 4 free body diagrams. I don't have a lot of space here for the net force diagrams, so maybe we can leave those out. Or maybe we'll do it for one of them. Okay, so, well, you see, here's the circle. Here's the center of the circle where I was holding on. And you see, at the top, gravity's perfect. It's pulling towards the center of the circle already, which means we don't really need any other forces there. This would be the critical speed at the critical speed, minimum speed also, to maintain the circle, where the tension would go slack, we would have no tension force at all necessary, and then it would continue around this way. Let's put it going in this direction. So here, it's on its way down. On its way down, we've got some tension towards the center, but force of gravity still pulling down. So we see that we have this keeping it going in a circle, but this is making it speed up. So it's going to speed up on this side. Here, gravity's going exactly the wrong way. So now when we say, all right, we need to have a force towards the center, gravity, what are you doing? Going the wrong way. So that means we need to compensate that with a really big tension force. Now this tension force here has to way overdo what's happening to gravity, or at least depending on the speed, right? Even if we're going at a low speed, it has to cancel gravity and more so that we have some force towards the center to keep it going in a circle. Here we're still pulling towards the center like before. So here's our tension there. And now you can see that in this direction, we have this tension, my bungee, pulling towards the center, keeps it going in a circle, but gravity pulling down, which means that's going to slow it down. And as you can imagine, if you look at the net forces of these, you've got this funny looking directions like this. But that's kind of not that helpful for us to look at those, because really what we want to look at is the two components. Gravity this way, slowing it down, tension making it go that way. Overall, the net force is this direction. But if you looked at that alone, you'd be like, what does that mean? Part of it is towards the center, part of it is straight down. Okay, at the top, we can say tension is 0. Now, let's just keep in mind here a couple of things.
One is that if we didn't go with the minimum speed, if I wanted to like be really crazy and spin a 5 kilogram mass at a much higher RPM, I would need, the faster you go, the more force towards the center you need. So I'd have to pull even harder, which means tension wouldn't be zero. It wouldn't be the minimum speed anymore. I would have some tension going down so that the net force towards the center would be bigger. And at the bottom, I would need even more, and maybe even snap my bungee, like what happened in my outtakes. So let's, kind of wrap it up there maybe. Maybe just do a couple quick things. Net force for this one would be, notice, also towards the center. Net force for this one is great. Oh, and how about, let's not forget how to do Newton's second law. It would be the difference of these forces. So I'm going to take the bigger one, take away the smaller one. And this could be our Newton's second law equation at the bottom. Little bit, it's not complicated, but you see, if you're going to try to solve a question using free body diagrams for a vertical circle, you want to pick the top where you only have one force, if t equals 0. Therefore, Fg is the net force because it's the only force. And this is why we got this thing for minimum or critical speed, m times g equals m times a. And you see from this we can see that the acceleration is actually just g, which means it's in a state of free fall, which is exactly what happens at the top. It's like, whoa, I'm free falling, until it starts to come down here, and the pull towards the center makes it go in a circle. But there's an instant moment there of free fall. And then you can solve this somehow. And oh yeah, don't forget we have this equation a equals b squared over r. So then if you solve this for v, we get this minimum or critical speed equation. Cross multiply the r over there, r times g, take the square root, and there's our equation for critical speed. That's where that comes from. Nice, nice, nice. In other words, the critical speed is the square root of just the radius of the circle multiplied by 9.8. Got it. Okay, that's a wrap, except I usually give some kind of secret. Well, I don't know. Shark fin pajama pants, pretty good secret. But while we're at it, let's go on a little tour here. I thought I could just show you a couple interesting things, like my solar panels. And by the way, this video is powered by totally clean, 100% clean, pure solar energy, because I use this, I got it feeding into a charge station in my house where I charge this phone battery and many other things. Cool, eh? And one more thing to show you quickly. Maybe you miss the fishes from school. Here they are. Hey guys. You guys surviving okay out here? I don't have a tank, and I normally would leave them at the school and take them home in the summer, so I need a little heater in there. And the pool noodles are there because I have to like seal them up overnight to insulate so they don't freeze to death, because we had some cold nights. And what? Cat food cans. Yeah, these fish are great at cleaning up my cat food cans. They get the scraps after my cats. Speaking of cats, hey squid, what you doing? You want to be on video? Oh, what a good boy. What a good boy. Can you do some kind of trick or something for the class? Oh yeah, who's a good boy? This is my cat Squid. He's very squishy like a squid. Yeah. Good boy. All right, Blue Veil. I think that's it for this long video. Take care. Take care, stay safe, and except for your family and pets, don't forget to social distance. Who's such a good boy? Who's such a good boy?